If the build-up shaft consists of a pipe from point A to B having an inner diameter of 25 millimeters and an outer diameter of 30 millimeters, whereas a solid rod from point B to C having a diameter of 15 millimeter as shown on the figure. In order to figure out the average normal stresses at point B and E of the axially loaded bar, we can start by writing down the key information in our data section. So since we are given the dimensions of the pipe having the outer diameter and inner diameter in millimeters, let's convert them and write those in meters so that we are consistent with our unit system. So the inner diameter is of 0.025 meters, whereas the outer diameter is of 0.03 meters. Next, for the rod section, that is from point B to C, we have the diameter of 0.015 meters. Now, since we are looking for the average normal stress at point D and E, this can be represented as sigma D and sigma E. And as we know that normal stress is equals to force over cross-sectional area, so we are basically looking for our force at point D and force at point E here. Now, in order to determine the force at point D and E, we can utilize our method of section, in which we will make a cut at these individual points and figure out the internal forces that are generated at that point. So to start, let us go ahead and select our point D first and start developing the free body diagram. Now, since we have made a cut at point D, we can select either one of the sides of that section. That is, either I can draw the free body diagram from A to D or from D to C to calculate the force at point D. Since it is easier to solve section A to D, that's why we are going for that. Now at point A, we have a load of 60 kilonewton going along the axis of the pipe, whereas we have made a cut at point D. So the internal load will become exposed. Let's write that in terms of variable FD. Now in this case, I have selected the internal force FD going away from point D. That is telling that the direction I have picked is the tensile direction. After applying our equilibrium condition and calculating the value of FD, if that direction is coming as negative, it just means that the force is compressive at our point D. So after solving our equilibrium equation, the value of FD is coming as negative 60 kilonewton, meaning that we have a compressive load acting at point D. Next, to calculate the stress, we just need to calculate the cross-sectional area of the pipe at point D. So we can do that by doing pi over 4 outer diameter is square minus inner diameter is square. Simplifying, we get the area of pipe at point D as 0.002158 meter square. Now, once we have the force and the area, let's take the ratio of these two and figure out our stress value. Simplifying, we are getting the value of stress at point D equals to negative 278 megapascal. Now again, here the negative sign is indicating that the stress acting at point D is in compression. Next, let's go ahead and figure out the stress at point E. Again, for the formula, it is force at point E divided by the cross-sectional area at point E. So to calculate the force at point E, again, we have to utilize our method of section. Let's create a cut at point E and separate the two halves. Now, in this case, again, I can select either a section from E to C or from E to A. Now, again, in this case, since from E to C, I just have one force, so it will be way simpler to solve this thing. So even just by looking at it, we can see that the force at point E will be equals to 20 kilonewtons, because they need to balance out in case of equilibrium, as the summation of forces along the axis of the pipe should be equals to 0. Simplifying, in this case, we are getting the value of Fe as 20 kilonewton as positive number, that is indicating that the force acting at point E is in tensile direction. Next, let's go ahead and figure out the cross-sectional area at point E. Since it is a circular rod, so area of the circle is utilized. Pi over 4d is squared, and the value of diameter was 0.015 meter here. Simplifying, we get the value of area as 0.0001766 meter is square. Next, let's go ahead and plug it back in our formula for stress at point E, and taking the ratio of force of 20 kilonewton and area of 0.0001766 meter square, we get our stress value of 113 megapascal. Now, in this case, since it is a positive number, it means that the stress is in tension at point E. Now, finally, let's go ahead and plot our volume elements and show how the stresses are represented on the cube here. Now, since in this case we just have the normal stress, meaning that the arrow direction will be normal to the face of the cube here. So for point D, since it is a compressive stress, the direction of the arrow goes towards the face of the cube, and it is identical on both sides of the face of the cube here as shown in the figure. Similarly, for point E, again the process is the same, but this time, since the stress is in tension, the arrow should be going away from the face. So our sigma E is pointing towards the right side of the face as 113 megapascal. Similarly, on the back face of the cube as well, it is going away from the face, showing it is in tension.